Hello, welcome to section 4. We're looking at exponential functions. Our first goal is to answer the question, what is an exponential function? They're brand new in intermediate algebra. Our second discovery will be the fact that a constant growth rate is all you need for exponential growth. If the growth rate stays the same, you've got exponential growth. And the third big goal in our first introduction to exponential functions is to see that whenever you've got exponential growth, you have a constant doubling time. So we're going to use the formula for accumulated interest. I say accumulated interest to explain that A in the formula. And notice how there's an exponent nt, and t is often our variable. We want to know what happens as time passes. And that variable is in the exponent. This is an example of an exponential function. Now, similarly, the formula for continuously compounded interest also has a t in the exponent. That e is a constant like pi, the r is the rate, the p is the starting value. But the point here is that the t in the exponent is a variable. That's how we can spot an exponential equation just by looking. So let's look at this first example. This is the graph of the amount of money in an account that earns interest at a constant rate of 15% per year. I'm going to emphasize that constant growth rate here. This is growing at a constant rate of 15% per year. And when you look at that curve, it doesn't look very constant. That's an exponential curve. So we started with $150 and it grew at 15% per year. Now, one of the big ideas I want you to get out of this is that the doubling time is constant. If you have a constant growth rate, then you have exponential growth, and the doubling time is constant. So the time that it took the account to go from $150 to $300 is the same amount of time as it took to go from $300 to $600, from $600 to $1,200, and from $1,200 to $2,400. That doubling time is constant. And I'm going to introduce the formula at this point because it's fine to say that the doubling time is constant, but it's nice to have a formula for that. And here it is. Not too long from now, we're going to derive this formula. We're going to actually use other equations to make it. Now, there's a lot going on in this formula that's new. For example, it's a time, but it's a doubling time. So notice how the subscript is the word double. You could use a capital T or something like that. This is the time that it takes something growing at a constant rate to double. Now, the numerator there is the natural log of 2, and that's a function. That's a new function to us. The natural logarithm's on your calculator. So this is the natural logarithm of 2. That's because we're doubling. If we took the natural log of 3, that would tell us the amount of time that it took for the amount to triple. Now, if you check out in your calculator, the natural log of 2 is approximately 0.69. So we can approximate this rule with a little bit of a shortcut, and that is 0.69 divided by the rate. Bankers use what's called the rule of 72, and that's, of course, an approximation for 69. So a reminder in this first sentence, for that reason, regardless of the starting amount P or the rate of growth R, all quantities that grow at a constant growth rate also have a constant doubling time. And because that's true, the doubling function, y equals 2 to the x, is an excellent place to look to understand exponential growth. We're now asked to graph the doubling function. Now, I use the phrase doubling function because that's exactly what y equals 2 to the x does. As you go to the right, you get twice as big. You go 1 unit to the right, and you're twice as big. Now, we can do this entirely arithmetically, and let's go through and do that to begin with. But then let's come back and let's look at what happens as we go to the right. Let's see that doubling in action. So when x is -5, we are doing two things. The negative says that that base of 2 should be downstairs, and the exponent of 5 says to multiply 2 by itself 5 times. 2, 4, 8, 16, 32. That 1/32nd, the 32nd because the exponent is negative. The negative says that the 2 should be downstairs. The 4 says to raise the 2 to the 4th power. 2, 4, 8, 16. You get the idea. The negative says that the 2 should be downstairs. The 3 says that we should cube it. 2, 4, 8. Same thing with the negative 2, downstairs, and square it 1/4. Simply take it downstairs, 1/2. 0, anything to the 0th power is 1. And now it's much easier to see that doubling happening. When the exponent is 1, 2 to the 1st power is 2. When the exponent is 2, 2 to the 2nd power is 4. When the exponent is 3, 2 cubed is 8. That's 2 times 2 times 2. And then, of course, 16 and 32. So take a look at this again and make sure that you can see that that doubling is taking place. As we go 1 unit to the right, we get twice as large. A 16th is twice as big as a 32nd. An 1/8 is twice as big as its predecessor. A 1/4 is twice as big. A 1/2 is twice as big as a 1/4. It takes 2 quarters to make a 1/2. It takes 2 halves to make a whole. So we are doubling as we're going to the right. You double 1 and you get 2. You double 2 and you get 4. You double 4 and you get 8. You double 8 and you get 16. And that should be, of course, a 32. So that 31 needs to be changed. And now we're asked to graph this. So here's a graph of y equals 2 to the x. Notice that as you go to the right, you get twice as big. Similarly, as you go to the left, you get half as big. Now, your response to this might be that there's not a lot of information on the left side, especially to the left of -5. It looks like it's right there on top of the x-axis. And then past positive, 3, it looks like it disappears up into the sky. Now, there's several ways of handling this, and one is the scale. If we really want to see what's happening on the vertical scale, we can scoot this whole thing down because there's nothing going on up at the bottom down there, so we don't need to see it. Something else we might want to do is simply rescale the y-axis. If we want to see more of what's going on to the right of, say, 3, we might want to make the scale of the y-axis different. Now notice that the y-axis is getting lots bigger than the x-axis, and that's the only way that we can see how this is doubling. Okay, welcome to section 9 in chapter 10. We're graphing exponential equations. Our 2 goals for this section are to identify exponential growth. That'll remind us of our first look at exponential growth way back at the beginning of the chapter, and to graph exponentials using the doubling time. So that's a little bit different, and so when we get to that, you'll see how elegant it is to use the doubling time to graph exponentials. We'll do the same thing for logarithms. Now, remind yourself of where exponential growth comes from. Exponential growth comes from a constant growth rate. So when I read this example, compare an investment of $1,000 that earns 5%. Now that 5% is a constant growth rate. And the moment you have a constant growth rate, you've got exponential growth. So the 5% growth rate is going to grow exponentially. We're going to compare that with an account that grows by $50 each year, and that's constant growth. So when we do that, we have, and this is the table we saw earlier, $1,000 is the starting amount at the beginning of our first year. We earn 5% or $50, and at the end of that first year, we've now got $1,050. Now that's exactly what happens in the first year, at least, with the constant growth amount. In other words, we added $50 to $1,000 and ended up with $1,050. But you can very quickly convince yourself that the constant growth rate requires the growth to increase. In fact, it's increasing fairly dramatically. We pretty quickly have an amount of growth that is twice what it was to begin with. I'm taking a look down here after 15 years. Instead of growing by 50, it's growing by nearly 100. And then after 24 years, it looks like it's growing by 3 times that initial amount. Well, the constant growth is still growing by 50. And remember how stark that ending amount was when we saw this before. 25 years later with constant growth rate, and we've got $3,386.35, and with constant growth we've only got $2,250. That's more than $1,000 less than what the constant growth rate account ended up at. Constant growth rates give you exponential growth. Now this is a section on graphing. So let's take those two tables that we just made, the constant growth rate, the 5% growth, and the $50 growth, and let's graph them. And we've seen this table before. We've now graphed it, and we can see time passing on the x-axis, so those are the numbers of years going by, and we can see the value of the account. Both of them are increasing in value as time passes. So the dashed line is the constant growth. That's increasing by $50 each year. The curved line is exponential growth. It's increasing by 5% each year. Now we can take the formula for compound interest, here it is, and we can plug in what we know about this equation. We know that the growth rate is 5%, so that's 0.05. We're assuming that the compound frequency is 1, that is n equals 1, and we get that the future amount, A, equals 1,000, that is the starting investment, times 1.05 to the t power. We say times first, but remember the order of operations. The exponent happens before the multiplication. So when you put this in your calculator, it knows the order of operations. It'll raise the 1.05 to the exponent first and then multiply by 1,000. So the time is t, but we want to see that on the x-axis. So we're going to replace the t with an x. And similarly, we want the future amount A to be our height. We want that to be replaced with y. So we're going to show this as an exponential equation in the way you'd expect to graph it. So the future amount A is now y, and t, the time, is now x. And that graph is a perfect graph, the solid line of the y equals 1,000 times 0.05 to the x power. Okay, now we're asked to graph the halving function, that is to take half as much as you go to the right. So what is this asking us to do? Well, let's do a little algebra and then let's look at the structure of this. And that little algebra says that when x equals 0, y equals 1/2 to the 0th power, which is 1. So we're going to start at the point 0, 1. Now, as we go to the right, as x increases by 1, the value of y decreases by 1/2. In other words, instead of doubling, it's halving. Also, as x decreases by 1, that is, as we go backwards, the value of y doubles. So the graph grows exponentially. Let's plot some points and let's see what's going on here. So again, we're going to start with -5. But now that -5 says that that 2 that was in the denominator would have been happier in the numerator. That brings the 2 upstairs and then raises it to the 5th power. Well, that's 32. And then next in that sequence, of course, as we're halving, when we go to the right, half of 32 is 16, and you can do the arithmetic to convince yourself of that as well. Half of 16 is 8, half of 8 is 4, half of 4 is 2, and then, of course, the point that we knew about to begin with, half of 2 is 1, and it continues taking half. There's a half, a quarter, an eighth, a 16th, and finally a 32nd. and we're asked to graph this as well. So here's the graph of the function that's half as large as you go to the right. The center of this world, of course, is the point 0, 1, halving as we go to the right, doubling as we go to the left. This looks a lot like a mirror image of the doubling function that we had in the previous question. And in fact, it is. It's a mirror image along that y-axis. And again, if you want to see more of what's going on here, perhaps to the left of -4, you're going to have to rescale the y-axis. That right side is already so close to the x-axis that if you want to see anything more going on, you're going to have to rescale. We're now at 1,000, and that probably illustrates the point that even down here at -10, we're at 1,000. So this rescaling really doesn't change the nature of the curve much. It's still growing really fast as you go to the left. Okay, and at this point, you can convince yourself that maybe the vertical scale isn't the problem. Maybe the horizontal scale is the issue. And so we remind ourselves that if you have a constant growth rate, then you also have a constant doubling time. And this is how we're going to graph these so that we can get good information without messing around with the scales too much and simply seeing what's going on with these. It says complete the table for the doubling time when $100 is invested in an account that earns 3.5% interest compounded annually. So the first thing we need to do is make this into an equation. I'm going to use the formula for doubling time. We introduced that right back at the beginning of chapter 10. The natural log of 2, because we're doubling, over the rate, 0.035. And when we do that, when we put it into our calculator, we learn that that's approximately 20 years. That top row is the value, and the value is doubling. So make sure that you look past just those first two amounts. 100 becomes 200. We doubled it. But now 200 becomes 400. We're not doubling the 100. We're doubling the 200. 400 becomes 800. 800 becomes 1,600. So that amount is doubling. And what allows us to do that is because we're going to use the doubling time. 20 years. It takes 20 years to double the first time. 20 years to double again, so now we're 40 years later. Another 20 years, 60 years after we started, it doubled again. And another 20 years, and we're at $1,600. So that's the structure of how we're going to graph these. We want the essential information from an exponential equation. In this next example, we're going to use x for t, so the horizontal axis, the old x-axis, is now our time axis, and we're going to use the y-axis will become our future amount a. We're going to begin with an investment or a starting amount of 100, and we're going to use the graph of the doubling function. Notice that in red, that's y equals 2 to the x. We're going to use that to graph the function that grows at 3.5% per year and starts with $100. So we're going to use the fact that we just found the doubling time, and let's start with that. So we start at time 0. The function doubles after 20 years. Another 20 years is 40 years later. Another 20 years is 60 years later, and then another 20 years after that. Now that means that our starting amount when the time was 0 was 100. After 20 years, so when t equals 20, we've doubled, and we've now got an account worth $200. But we can continue with this. It doubles again in another 20 years. So 20 years after that, 40 years from when we start, it's doubled again. And of course, when you double 200, you get 400. So after 40 years, we now have $40. And you see where this is going. After another 20 years, that is, after 60 years, we've doubled again to $800. And then after another 20 years, we've doubled to $1,600. So notice that this curve gives us a lot of information about doubling time and about the future values. 80 years from now, that $100 account will be worth $1,600. Now, if nothing else, this illustrates the importance of having a formula just for the doubling time. We've been using it. In fact, I introduced it right back at the beginning of Chapter 10. Now we're going to derive it. Derive means to use something we already know to make some new information. We're not proving it. We're simply showing that it is consistent with things that we've already been assuming. Well, what have we been assuming? We've been using the formula for continuous compound growth, A equals P times e to the RT. Now, that tells us that if we know the current amount, P, and the future amount, A, we can go through and do the algebra. When we're doubling, what we're saying is whatever the current amount is, whatever P is, the future amount is twice that. So we're basically saying to double means that the future amount is twice what the current amount is. So let's plug that into our formula. Taking the place of A is 2P because we're asking the question, how long does it take to double? Now we see P as a factor that is attached by multiplication on both sides of our equation. So we're going to get rid of it by dividing, and that'll take both of those P's with it. Now we've got 2 equals e to the RT. We're going to solve this by taking logs. We're going to take the natural log of both sides. You could solve this by translating as well, but we're going to do this algebraically by taking the natural log of both sides. On the right side, two things happen. The exponent becomes a coefficient by the power rule, and the natural log of e goes away. So we've got the natural log of 2 equals RT. Now, if our goal is to find the amount of time it takes to double, we want to solve for t. It's attached to the r by multiplication. We can undo that multiplication with division. We're going to divide both sides by r. Now, you can do this two different ways. You can say that the time to double, and we're using subscript here to say that, is the natural log of 2 over r. Or you can just take a little bit of a shortcut and call that a different flavor of t, maybe capital T. So now it says, as the pollution from automobile grows at 7% per year, how long until the amount of air pollution doubles? So we're going to use exactly the formula. We're going to plug in what we know. It says that R is 0.07. So we're going to plug this into our calculator, and we get 9.9021 rounded to 4 decimal places. Then we can say that's approximately 10 years. It says that the profits of a major corporation grows at 11% per year. That's our constant growth rate. How long until the profits double? So the same routine, we're going to plug it into our formula for doubling time. So taking the place of R is our constant growth rate, 11%, written as a decimal. Put this into your calculator, and I really recommend that you're able to do this in your calculator, and you'll get 6.3013. And we could round that to about 6 years. The profit of this corporation doubles in 6 years. Credit card debt grows at 18% per year. How long until the debt doubles? Same routine. We're going to use the doubling time. We're going to plug in 0.18 as the decimal form of the constant growth rate. We're going to get an approximation out of our calculator, 3.8508. And it looks like that rounds to about 4 years. Another 70 years, and it will have doubled again. That's after 140 years. Add 70 more years, and you get 210 years. Another 70 years, and 280 years from the time we started. So let's take a look at this curve. This curve is y equals 2 to the x. It's interested only in doubling time, and we know the doubling time. Starting at time 0, 70 years later, it's doubled once. Another doubling from that previous amount, it's actually 4 times larger from where it started at year 0, at 140 years, 210, 280. We started with 4,500. We doubled that, doubled again, and doubled for that last time. Okay, our last example in section 9, we're looking at a population that is decreasing. It says to graph the population of a small town over time as its population decreases from a starting population of 3,408, and it's decreasing by 2.5% per year. So let's first look at the populations, at y. It starts at a population of 3,408, and it falls by a half. So we divide by 2, and then divide by 2 again, and then divide by 2 again. Now, for the times, well, we start at x equals 0. Then we compute the doubling time. We use the formula, natural log of 2 divided by the rate. And we see that the doubling time is about 28 years. So another 28 years passes, and the population has fallen in half. And it continues in that way. Another 28 years, so we add 28 to 56. And we take the 852 and continue dividing it by 2. Another 28 years, 112 years from when we started, and the population has fallen in half yet again to 213. So we put this information on our graph. So starting at time 0, it's 28 years to double. 56 years after that, 80, or after where we started, 84 years from when we started, and 112 years from when we started. The population starting at 3,408, then half of that, 1,704, half of that, 852, half of that, 426, and then finally, after 112 years, down to 213. Radioactive material decays in similar ways, but I like talking about population. And that concludes section 9.